Hello and welcome to the 11th lecture in chapter 22 in our comprehensive course on AI, ML and DS. Now, in this lecture, we want to talk about part E and the last part of the chapter, Introduction to the Scikit-Learn Library. If you remember when we began the chapter, there were 5 parts. Creating new features. The name of the chapter was Data Pre-Processing for Machine Learning. And as I said, that data pre-processing is feature selection, feature engineering, etc. So one was creating new features. Second part was scaling the data and doing normalization. Then third part was introduction to feature selection techniques. Then fourth part was model evaluation and validation techniques. This much is already completed. And now part E, that is introduction to Scikit-Learn Library, right? So let us continue with this portion. Now, earlier when we made one model using Scikit-Learn Library, then I told you that the output of the model which is created, that itself is such that you can directly go to the documentation of the library, right? So, this was somewhere here, linear regression model. And if I click on that question mark like symbol at the upper right corner, then I can go to the documentation. This is old documentation, so switch to stable version, and I can get various features of Scikit-Learn library. Now let us read this part and let us see that each feature is already covered by the documentation. So that means once you have just make a cursory glance through the documentation, then you don't have to remember anything. The Scikit-Learn library is a powerful Python library which is used for implementing machine learning algorithms. It is built on the top of NumPy, SciPy, and Matplotlib, and it offers a wide range of tools for model building, training, evaluation, and with a focus on machine learning and statistical modeling. Now, that means this library, Scikit-Learn, is very thoughtfully made. It is made in such a manner that it nicely complements the earlier learned library, because earlier learned library were good for previous stages of data science lifecycle. For example, data acquisitions, then we know that we use pd.read_csv or pd.read_excel for reading various kind of data, loading the data. Okay, then later on we did exploratory data analysis, for which also Panda, NumPy, Matplotlib, then Seaborn and Plotly library was done for visualization and exploratory data analysis. Then we did feature engineering, for which also these same libraries, NumPy, Pandas, etc. were enough. Between these two, there was that small but very important phase that was about statistics, and also that was about hypothesis testing, and that used the SciPy and state models library. Now, these libraries can do everything up to this stage of machine learning lifecycle, feature engineering, but they cannot do model creation, right? In fact, some of the feature engineering processes also, like test, train, split, model creation, which makes the feature engineering process more robust, and feature selection process more robust. For example, making a plot of the most important or features, etc. For that, we already used the Scikit-Learn library in earlier lectures. That means that Scikit-Learn is now going to be used further more and more, and then creating the model, then training the model, validating the model, deploying the model by creating a pipeline, all those things. There, the Scikit-Learn comes into picture. So it is a complementary to Pandas, NumPy, and then Matplotlib and all that. It does not mess into their work, but it at the same time complements them. And second advantage is it is built on the top of them, so it is perfectly compatible. That means that whatever output format, data formats that are given by the results of those Pandas, NumPy, etc. libraries, those output formats are clearly directly usable on that model creation and training, right? For model creation and training by Scikit-Learn. So that is perfectly compatible with other older library. You don't have to build everything from the scratch. Your older libraries, Pandas, NumPy, they will work perfectly. Okay. Now, here we want to talk about that Scikit-Learn library. It has a wide range of tools for building, training, evaluation. Okay, what are the core features? Then it provides features for pre-processing, model selection, supervised learning algorithm, unsupervised learning algorithm. In fact, it also provides semi-supervised learning algorithm, then various metrics for evaluation of model, and the various functions for creating pipelines. Now, do I have to remember all this? No. So we have seen earlier that one such linear regression model even created, if I click on the question mark, it takes me to the documentation part. And in the documentation only, everything, all the features of Scikit-Learn, they are already there. For example, it can use to create clusters. So I can open that in new tab, and you can see that various types of clustering like k-means clustering, HDB scan, DB scan. We are going to study the clustering in much detail later on. So don't worry at present. Then hierarchical clustering, word tree, that all these things are there in Scikit-Learn. Similarly, there is another, for example, if I show you, then data sets. So it can provide several ready-made data sets like this clear data home, then dump SVM light file, fetch 20 news groups data, then other, for example, fetch California housing somewhere that we had used, okay, and load wine data set, then breast cancer data set, diabetes data set, then uh, for and there can be more also if I click on this next. So it will load iris data set, which we are going to use just now. Okay, so it can provide data sets. Okay, fine. Now what more it can provide? Let us see. It can provide this linear discriminant analysis, which is a dimensionality reducing technique, just like PCA, principal component analysis. I'm going to explain what is PCA in this chapter only, this lecture only. So wait for a minute. And this ensembles. So again, I'm opening in a new tab, and then ensemble it can get various boosting and bagging type of algorithms. In boosting, it can create ADA boost, and then in bagging, various bagging regressor, gradient boosting, that XG, and then uh, sorry, GB, gradient boosting, and then if you write extreme gradient boosting, then that would be XGB, right? Then maybe random forest, which we have seen one of the very popular algorithms. So various ensemble algorithms are used, are provided by scikit-learn. Then there are some tools or functions for feature extraction. Then there are some tools for feature selection. So sklearn feature selection, for example, recursive feature elimination, then chi-square, F classification, that is ANOVA for feature selection, and all those things, right? Then there are libraries for imputation. Imputation means replacing the null values by some other. For example, these two are very frequently used in data science: simple imputer and KNN imputer. So they are very frequently used. Okay, so scikit-learn also provides libraries for imputation. Then linear models. So again, that linear model is a category in which logistic regression, then linear regression here, then reach, lasso, all those things are already there. Elastic net, lasso, all those things. Okay, so that is one big category of linear models. Then there is model selection. So it helps for selecting appropriate model by k-fold validation. Then leave one out stratified k-fold, CV, check CV, etc. Train test split, which is practically used in each and every supervised learning problem. So that is provided in model selection. Then multi-class classification libraries, neural network library, naive Bayes, which is one of them, this pre-processing. So that is this, that is binarizer, then label binarizer, label encoding. Some are min-max scaling, normalizer, one-hot encoder. Some are familiar terms. Okay, so all those facilities are provided by sklearn. Then one more is pipeline creation. What is pipeline? That is coming in this chapter, but in short, you can understand that it saves the labor of the data scientist a lot, and it helps the data scientist to uh, you can say that use the earlier created code for analyzing similar data, that is with same feature and same data type but new values quickly. Okay, so in short, it is one sentence. It is often said that pipelines make data science reproducible for this using sklearn pipeline module. Okay, then this SVM, semi-supervised learning, all those things. So now if I read this, then everything will become clear that, oh, these are the features which sklearn provides. Okay, pre-processing. So I showed pre-processing here. Okay, then model selection. So I showed model selection and model validation here. Then supervised learning algorithm. Now supervised learning is not shown as a separate category, but all these linear regression, then ensembles, that is this random forest, XGBoost, these are all supervised learning algorithms. Then unsupervised learning algorithms that are those clustering, etc. And even that algorithms are also provided by, here this is already open, sklearn cluster. Okay, so dbscan, then k-means clustering, all types of clustering. Metrics for model evaluation, perhaps that is not open, right? So that is also there, that how can I evaluate my models. So for that I have one library which is sklearn dot here I'm trying to find metrics. Yeah, okay, so various metrics for classification. These are the metrics: accuracy, AUC, etc. You have not seen them so far. And for regression, these are the metrics: mean squared error. So these you have seen. Then root mean squared error. This, then R square. These are some things which you have already seen. So metrics it provides, and finally it provides pipelines. So pipelines are this thing: make pipeline and make union. So in short, just look at this documentation and you will get all the features of scikit-learn. This is one of the best documentation of all Python libraries as far as my opinion is concerned. Okay. Now, what are commonly used modules among them? Then data sets for importing data, pre-processing, for scaling, centering, normalizing, binarization, that is encoding, converting categorical data into numerical data. Okay. Model selection for fitting, then train test splitting, cross validation, linear model for linear regression, logistic regression, cluster for clustering, metrics for evaluating the model, and so on. These are very commonly used. Now let us take all these. I mean, no need to remember them, as you use scikit-learn again and again, and you will have to use it again and again in subsequent chapters. So then this will automatically be remembered that, oh, these are the various functions which scikit-learn provides. So now let us take one example, and this example we will take such that it will cover both supervised learning and unsupervised learning also. So let me quickly discuss what is this supervised learning, this particular diagram. As such, this semi-supervised and reinforcement learning, they are also there, but say at present we want to make our discussion simple, so we will talk about these two only. So supervised learning, for that I will use this our familiar diagram, that this is our data set, and our data set has feature matrix and the response vector. Response vector is also called label. We do a horizontal split, say 80% or 70% data in the X train and Y train, and 30% of the data is in the X test and Y test. Okay, and then we say that we train our algorithm using chosen model or chosen algorithm, say linear regression or random forest, and while training we use X train and Y train. That means what? That my training is happening under the supervision of these labels. Y train is what? The values of the response variable for these values of the features, right? So if these are say 10,000 rows, then for each row I know the values of the features, and I know also the value of the response variable. So that is called label. Value of response variable is called label, and I feed them both. That is the question and answer also, both, something like that, or I feed them data as well as the corresponding insight also. But my purpose is not to make prediction on this data, so I just feed both data as well as what insight is already obtained from already earlier known data, and that my model tries to infer some patterns, that okay, this type of features are there, then this is the inference, these type of features are there, then this is the inference. So that means there is some this kind of pattern between the features and the inference. So when it passes through all the features, all the X train and corresponding Y train inferences, and then it will learn all the patterns, then we will say that it is a trained model. Once it is a trained model, then we use it to make predictions on this X test. At that time, we do not use this Y test at all, and on X test it makes prediction and gives Y predicted. Okay, and then we compare the Y predicted and Y test with each other to know how accurate our model is. So that type of learning, that is called supervised learning, because here during the training set you have to provide the levels or Y train. That means learning is happening under the supervision of the levels of the train set. Okay, so supervised learning. But there are certain types of data in which there is no supervision at all. For example, that is, for them this kind of data set is not there, but only this green portion is there, only features are there. There is absolutely no target variable. Okay, so you are not trying to predict anything, you are just trying to study various features in each record, each observation, and based on the features or traits or values in the columns, you try to group these. Say these are 9,000 rows, then you try to group them into 3,000 rows or 3,000 data points in one group, 3,000 in another group, and 3,000 in another group. And the number also may not be exactly equal. It is possible that 4,000 in one group, 2,000 in another group, and 3,000 in another group. That makes total 9,000, right? But you are trying to group your data based on certain traits, and similar traits are put in one group. For example, this is the data of customers only on your online portal, and this first column is the age of the customer, second column is the maybe marital status of the customer, third is the gender of the customer, fourth is the purchase, the total purchase which the customer made in past 6 months, and fifth is suppose the mode of payment, whether cash payment was made or credit card through account, what kind of payment was used. So suppose I get that out of 10,000 there are around 3,000 customers or 4,000 customers which are such customers whose age group falls in 15 to 20, whose gender may be male or female both, but who are pretty young people, so they are not earning themselves. Therefore, most of the time these customers pay in cash. They may not have credit card, etc. So they pay in cash. Cash on delivery option is chosen by them, and they also buy less amount. So in last 6 months, their bill ranges from say $10 to $25, like that. So they buy small items. Okay, and those all 6,000 rows which fall under this trait, they are put in this group. For example, this brown colored group on the leftmost side where my cursor is at present moving, right? Similarly, there are some 3,000 more customers who are in the age group of 25 to 45. That is the prime earning age for a person, who always pay through credit card, whose last 6 months uh, purchase is also substantially high, maybe $100 to $200 bracket, and they buy all kinds of things like household things to electronics to laptops or laptop accessories and all those things, right? So those type of customers, they are put here because they are valuable customers because they buy more and buy more frequently. And then these are another kind of customers, so who mainly suppose buy only household items. Mainly they do shopping in the afternoon time, so which is the standard time for housewives because they become free in the afternoon and open the internet and do the shopping for household items. They buy mainly clothes, then house accessories, etc. And they also prefer to pay by from account, or they also buy reasonably moderate amount, maybe in last 6 months around $50 to $100 like that. So they fall in this third category. So here there is no target variable. This yellow portion is completely absent. Only based on given data, I found out three groups, and three is just an example. It can be four groups or five groups or two groups, but I found out distinct groups having totally different traits or characteristics. Then this process is called clustering. And here there is no target variable, so there is no question of training being done under the supervision of target variable. Okay, so that type of training is called unsupervised learning because there are no target variable, there is no question of supervision, right? So we will take one example on supervised learning and we will take one example on unsupervised learning. Clustering is an example of unsupervised learning, and similarly, random forest or XGBoost or simple linear regression, all those, they are examples of supervised learning. Okay, and we will take the data set also from sklearn library only. We take the entire example is made such that everything is from sklearn only except this one use of NumPy, right? So from sklearn, we use this, we import the iris data set. About iris, we have seen that it is a kind of flower, and this smaller kind of leaf that is called petal, and petal width and petal length, these are two parameters. Similarly, this large leaf in every flower, that is largest leaf, that is called sepal, and this is sepal length, and this is sepal width. Then using these four parameters, petal length, petal width, sepal width, I can classify this iris into three species. One is called iris setosa, one is called iris versicolor, and one is called iris virginica. So this is that data set. This is from sklearn model selection, train test split, and grid search CV. Pre-processing, I am importing standard scalar. From sklearn.decomposition, I am importing PCA, principal component analysis. From sklearn.clustering, I am importing k-means for this kind of clustering, unsupervised learning. From sklearn.ensemble, I am importing random forest for this kind of model, supervised learning model. From sklearn.pipeline, I want to make a pipeline so that I don't have to repeat the same process again and again and again. And finally, this is a classification report because ultimately this is a classification task. Suppose there are 900 rows, then it might be possible that 500 are setosa, 300 are versicolor, and 100 are virginica. So accordingly, I want to show them on these three on this axis. Classification can also be done by supervised method. Random forest can do the classification. At that time, such line of separation is obtained, and two classes. This is class A and this is class B. I should have shown by different color, but okay. Then these are two different classes, and they are separated by this line. At that time, target variable will be required, labels will be required using random forest. But it can also be done by k-means, and at that time, no target variable will be required. Only the sepal length, sepal width, petal length, and petal width of those 900 records will be required, and based on which three distinct groups will be created. One will be setosa, one will be versicolor, and one will be virginica, right? So this is how the problem is set up. Now data is load underscore iris. So let us load, and I am dividing x into x and y. X is data.data, and y, that is my label variable, that is data.target. Okay, first previous one has to be executed. So execute previous one and then this. Now x and y are created means in this diagram I am already here. Green portion is created and yellow portion is created because I want to give example of supervised as well as unsupervised. So yellow portion will be required, labels will be required for supervised. Okay, so now let me print. So this shows that there are four parameters for all observations, and this is sepal length, this is sepal width, this is petal length, and this is petal width. Okay, and if I print my y, then that will show me the corresponding species. However, it does not show the species in words, setosa, versicolor, virginica, but it shows the encoding of it. Say setosa is 0, versicolor is 1, and virginica is 2. So if you see here in the y, then you will see zeros. So all these are records are setosas, then ones. So all these records are versicolor, and all these twos, which are the records for virginica, right? So fine. Now I am clearing this because I want space and I don't want to scroll down so much. Now I am already having this stage. I have x separate and y separate. Now I am doing this stage, that is horizontal splitting. I have done that so many times. So you know that four things will be produced: x train, y train, x test, and y test. How four things will be produced? By applying train test split to what to feature matrix big X and target vector small y, and you can select some test size maybe 30% or 0.3 and random variable seed or random state, right? Okay, so we have already imported train test split earlier, so now that we are using, okay, here you can see that we have imported it. So let us use that train test split, and I will get x train, x test, y train, y test. So that means now I am in this stage. That means I have four groups from my original this kind of data. Okay, these diagrams I have kept just for explaining what is principal component analysis, because I am initializing one standard scalar that also I have imported somewhere here from sklearn.preprocessing import standard scalar. Okay, and I have also initialized I'm also initializing one PCA, which is PCA in bracket n components is equal to 2. Okay, now what does this PCA do? As such, we are going to have a very detailed discussion on principal component analysis at present, later on in other chapter. But that for at present we will just do what is required. Okay. So what PCA does is, suppose I have one simple two-dimensional case in which my y response variable is on y-axis and there is only one x1 as the independent variable or feature. So then the model will be very simple. Y is equal to beta 0 plus beta 1 x1 plus or minus some error, right? So it is easy to show that kind of model on a diagram. So these are my data points, and I'm showing my model on two-dimensional diagram. Even if I would have two features, x1 and x2, okay, still I could have shown it on a diagram with some effort. For example, here radio marketing expense is TV marketing expense is on this x-axis, and radio marketing expense, that is another feature which is on z-axis, and this y-axis is the sales of the company. So in that case, the whole data points, all data points, they are spread in the 3 dimensions, and I have to pass a plane for classifying these data points into 2 distinct segments. Okay, but the question is what to do if there are more than 2 features. Then I cannot draw even this kind of diagram, and there can be sometimes even 5 features, 10 features, 50 features, so many features, right? So this is some example of that kind of data set. This is the diabetes patient's data set, and it has these many features. Index is not a feature column, but age, sex, gender, that is BMI, BP, 4 columns, then S1, S2. There are some other features, maybe some clinical measurements of that patient. So S1, S2, S3, S4, S5, and S6, right? So these total 6 and 4, 10 features are there. Now, can you draw this all 10 features on a diagram? Then it is not possible, right? 10-dimensional space. You can imagine. You can even do maths on a 10-dimensional space, but you cannot draw a 10-dimensional space. This is a 3-dimensional space which you try to draw using this kind of inclined lines and all that. Okay, that on a 2-dimensional page. But 10-dimensional is totally out of question, right? So at that time, what you have to do is you have to somehow convert this data, which is at present spread over 10 columns, into some simpler data, which is spread only over 2 columns, like maybe this kind of data, okay, where this one column is named, suppose P1, PC1, principal component 1, and this other column is called PC2. So somehow I have to convert my original data 0, 1, 2 are index numbers, these, but these 6 columns should be replaced by only 2 columns, PC1 and PC2, and still all the information of this should be retained in those 2 columns. Now when I say all, some information will always be lost when I reduce the dimension, that is the number of columns, by from 10 to 2, but still majority of the information, if I can retain 95% of the information or 93% of the information, then I would say that 2 principal components are retaining most of the main information. That is why the name is principal. So PC1 means principal component 1 and principal component 2. So you can say that principal part of the information contained in this 10 columns is already captured by these 2 columns. And then you can take PC1 on x-axis, PC2 on y-axis, and plot same data points which were originally in this value, that you can instead plot using the values of PC1 and PC2. So you get this orange colored data point. And then there is one technique called biplotting. So you can even get where those 6 column headers will be, that is age, sex, etc. You can see here age is there, here sex is there, here BMI is there, here those S1, S2, S3, all those things are there, right? So you can get one 2-dimensional representation of a 10-dimensional data. That process is called principal component analysis. And as I said, we are going to learn that in much detail. So at present, don't bother how it is done. But say there is a miracle by which 10-dimensional or 10-column data sets can be fairly accurately represented by a 2-column data sets. Okay. So I have to explain that because here we are using that PCA is equal to PCA and components is equal to 2. So that means two principal component, PC1 and PC2. Now it is not necessary that it should be always 2. It can be 3 also. So at that time it would be that kind of diagram which we had seen, PC1, PC2 and PC3. Okay. So that is this kind of diagram. One axis will show PC1, one axis coming out will show PC2, and one axis going upwards that will show PC3. Okay. But normally two components are preferred because it can plot the diagram easily. Now, so what we are doing in the first step, we loaded the data. Now forget about this explanation and all that. I'm just showing to bring the continuity. We imported libraries. We loaded iris dataset, X and Y part, or that is train and test, not train and test, sorry, just X and Y part. Okay, and that is features and target variable. Then we splitted both parts so that we got train and test for features also and train and test for target variable also. Okay, now this diagram just shows principal component analysis. Then we initialize one scalar object using the standard scalar library which we imported earlier. Then we initialize one PCA object which will automatically do the principal component analysis using PCA library from Scikit-Learn. Okay, and then we initialize the random forest classifier. So random forest classifier is equal to random forest classifier, random state is this much. So at that time we are doing supervised learning because as I said, random forest classifier requires a labeled data because we train the model on X train and Y train, and then we test the model on X test, and whatever predictions are coming, they are compared with the labels of Y test for deciding the goodness of fit. So labeled data is required. So supervised learning example this is right now. So we initialize one supervised learning classifier, random forest, and one unsupervised learning method also classifier also we are in that is k-means for clustering, because clustering is also in one-way classification only. You can see that if I can show the three different types of flowers by three different types of dots like this on the same page, setosa is here, versicolor is here, versicolor, and marginica is here, then in that case I have classified them. Okay, so that we are doing, that is unsupervised classification, and that we are doing using k-means. You can decide the number of clusters. I have kept 3 because I have 3 species, but you can keep 5, then 5 such groups will be created. You can keep 2, then 2 such groups will be created. So I have to think that what are the total number of classes that I have, and accordingly I will keep the number of clusters. Now once this much is done, so these steps are common for up to this, all steps: import library, load data, then split it into train test, and create a one scalar and one PCA object. That much steps are common for all. Then if you are doing supervised, then do random forest. If you are doing unsupervised, then do k-means. Suppose I am at present doing supervised, so for a moment let us completely forget about that k-means, okay, and focus only that we are doing random forest. So after scalar object is initialized, after PC object is initialized, and after my random forest model is initialized, I have to use them to create a pipeline. So pipeline, where what is, from where the pipeline keyword is coming, we have imported it. That is here from sklearn.pipeline, import pipeline. So pipeline, and in the pipeline, what are the components? Then first there will be scaling, because PCA, whenever we will learn it in detail, you will see that it cannot work without a scaled data. So for principal component analysis, standard scaling is must. Okay, so on the pipeline, first scalar is object is put, then PCA object is put, and then random forest classifier is put. What is the meaning of word pipeline? It is just like our water pipeline or that kind of pipeline, so that from one side data will enter, flow will enter, and from other side flow will exit. So what will enter is data. Then what will happen to that data? First the data will be scaled using standard scalar. Then what will happen to the data? Then from the original data, which might be like 10 column data or 20 column data like this, multi-dimensional data, it is converted into this kind of data, 2-dimensional data. Okay, so how it will be done? Then it is n components is equal to 2 principal component analysis. And once that is done, then so in the pipeline, first scaling is done, then converting multi-dimensional data into 2-dimensional data is done, and then random forest classifier is applied. So let us show this pipeline, and of course here somewhere I think I have to initialize this thing. Okay, so if you initialize, now this Scikit-Learn has nice thing that it shows the pipeline by a nice picture, and if you click this black horizontal arrow, it becomes vertical, and that means it has expanded, and you can see your entire pipeline. First scaling will be done, then PCA will be applied, and then random forest classifier would be applied to the incoming data. Okay, and it is even giving me details also that scaling will be done by what method? Standard scaling. PCA will be applied. How many components will be created? 2 components will be created. And classifier, random forest has what random state? Then 42. Okay, and this is the expanded form of my pipeline. The advantage you can immediately see that if you now next, we will save this pipeline in normal data science flow. Once the pipeline is created, we will save it as a pickle object. and we'll say that save supervised pipeline dot pickle and as right binary, okay, and then we will save it as, and next time when same data comes, same means not the values are same, these inner values may change but same features are there and same data type is there. So but new patient, new another 100 patients data comes, so at that time I just have to load the pipeline which I have saved as a pickle model in my environment. So load that pipeline and apply that pipeline on the new 100 models, okay. So that is the meaning of word reproducibility. Also, this is important thing that during the creation of the model or training of the model itself, we are doing some parameter grid for grid search CP. Now, what is this grid search CP doing here? Then this is random forest. So random forest means it is a forest of several decision trees. Okay, what is a decision tree? A decision tree is somewhat like this. For example, this is suppose a decision tree for patient diagnostic system where at the root node, this is called the root of the decision tree, and at each node the bifurcation occurs into two parts and a decision is taken inside the node, and accordingly the control moves either in this direction or in this direction. So the two directions are mutually exclusive at any particular for any particular observation. So at root node some new patient's data comes, and first question here is ask gender. If the patient is male, then go on this line. If the patient is female, go on this line. Second question is asked at the second node. Is diabetes positive? If it is yes, go on left side. If no, then go on right side. Third question which is asked is, what is BMI? If BMI is 45 or say greater than 40, then that means the person is obese. And then you will say that his risk of developing cardiac condition, stroke, etc. is high. So he is at high risk. But if he has diabetes, but his BMI is only 22, so that is fairly thin person, and that means that he may not have cholesterol and other complications. So you can say that his this risk is moderate. Moderate risk still remains because diabetes is still there. Okay, he is not obese, but moderate risk remains. Okay, then here the question was diabetes yes, then I went on this path. But if diabetes is no, again the same question is asked, what is BMI? If BMI is say 60, which is tremendously high value, so person is very obese, and then you will say that the risk is high, even though there is no diabetes. Okay, and but if there is no diabetes and the risk and the BMI also is 21, so in that case I would say that this risk is very very low because no diabetes also and no obesity also. So the risk of cardiac problems is very low. Okay, so this is how decisions are made, and actually for healthcare applications, decision trees are very highly preferred because the reason is the easy explainability. This is exactly like the process by which a doctor thinks about symptoms, and then if this symptom is there, yes, then go in this direction. Then if this symptom is there, no, go in this direction, like that. And finally, he arrives at some diagnostic judgment. Okay. So many decisions in our life we take in this manner. This is called decision tree. This node where the decision tree begins, that is called root node, and this node, that is where the dividing into two parts, branching stops, that is called leaf node. So whole tree is actually inverted tree. That means like this kind of tree, right? So it is this kind of tree where whose root is at top and whose leaves are at bottom. So root is like this. These are roots which I am now drawing. Okay, and these are some leaves. Okay, so you can see that this kind of inverted decision tree is created by this decision making structure. Now what is ensemble? Ensemble is collection of many such trees. Random forest, name itself indicates that forest is collection of several such trees. Okay, and now how many such trees I want to make? Then I want to make a total 12 trees. How 12 trees? For estimators, that is number of trees, I am keeping three choices, 50, 100, 200. And for max depth, what is depth? The depth is, max depth is the distance between the root node and the leaf node. That is called max depth. So for that I am keeping four choices. None. None means no limit to the depth. So go on extending your tree downwards until all the diagnostic questions or all the branching questions are exhausted. Okay. And then 10. So sometimes it is possible that if you allow your tree to grow up to the last question, so at that time it might have 200 height or something, so it will be very long tree. But if you keep this max depth 10, then after 10th bifurcation, here this at this level, at this level it is called depth 1. At this level now it is depth 2, and at this level it is depth 3. So if I keep n depth is equal to max depth is equal to 10, that means there will be 10 such bifurcations will be present. Okay, and the 10 that is 10 layers will be present. Then 20. So that tree will be further longer. So 20 such bifurcations will be done, and 30, so that tree will be further longer, right? And instead of estimators also, you can take 50 and 100, instead of 50, 100 or 200 trees together make one forest. So this is what the number of trees in one forest are: 50, 100 or 200, and this is what the number of nodes or the depth of the tree in each tree. Okay, so how many such forests can be made? One forest will be 50 decision trees with unlimited depth. Then one is 50 decision tree with 10 depth. One is 50 decision tree with 30 depth. Then 100 decision tree, unlimited depth. 100 decision tree, 10 depth. And 100 decision tree, 20 depth. And 100 decision tree, 30 depth. And same with 200, right? So that means total 3 multiplied by 4 or 12 will be provided. Now, if you do this, then parameter grid you have tested. So what this grid search CV does is it makes your modeling very robust. First, instead of single decision tree, you are using a forest in which minimum 50 estimators will be there and maximum 200 estimators will be there. So 200 trees or 50 trees at least will be there. Okay. And even among forests, you are not trying one forest, but you are trying 3 multiplied by 4, 12 different types of forests. And then whichever forest gives the best possible accuracy, you will select that hyperparameters. So that means that many estimators and that many number of depth and max depth. Okay. So grid search CV is equal to grid search CV into pipeline supervised. What is pipeline supervised? This thing: scaling, applying PCA, and then applying random forest. Pipeline supervised will be applied using what? Using this parameter grid. So that means random forest will not be just one random forest, but it will be in the pipeline supervised. There is random forest at the end, right? But it will not be just one random forest, but 12 different random forests will be tried. And even in that, the trained data set will be divided into 5 folds cross validation. We have done earlier 5-fold cross validation, so we know what it is. So that means this kind of 5-fold cross validation will be done, and the average performance will be found for each forest. So 12 forests and 5-fold cross validation for average performance, that will give the accuracy for that forest, and then best accuracy will be given as the output. Think if you try to do this all manually, then how much time it will take. But fortunately, Python and this scikit-learn is so powerful that it handles everything automatically, right? So grid search is equal to grid search CV pipeline supervised. That is this pipeline which does 3 things. It scales the data, it applies principal component analysis, and then it applies random forest classifier. Okay, and how classifier random forest will be applied as per this parameter grid. So that means, as I said, 12 forests will be tried one by one: 50 with none, 50 with 10, 50 with 20, 50 with 30, 100 with none, 100 with 10, 100 with 20, 100 with 30, and so on, right? Okay, and CV is equal to 5-fold cross validation. Once this grid search model is trained as per this pipeline, that means this many stages are done internally, and as per this parameter grid, that means this many options are tried during each stage, then that model is fitted on X-train and Y-train. So that means you get trained model. That is this thing, X-train and Y-train, and they are used for supervised learning, and you get a supervised learned model. Okay, so you get a trained model. You will also get the output of best parameters, and you will get what is the best metrics for that model. Okay, now parameter grid is not defined, so I have to execute this, and then this takes some time, because I told you that it tries 12 forests, and in each forest it further tries 5-fold cross validation. I have powerful hardware, so it took me only this much time, but in your case it might take even more time, right? And I got that the best parameter are max depth is none and number of estimators 50. So which forest gives the best result, best classification? Into Setosa virginica and versicolor, that's a forest with 50 trees in which max depth is unlimited. Okay, and what is the best score for that best model? Then 89% is the cross validation score, 0.89, right? So it is a reasonably good model with 89% accuracy of classification. Now let us actually classify. So that means in our this process, somewhere earlier I had tested one diagram, this diagram, that once the model is trained, what you do, you take that trained model and take the X test, apply the model to X test, and predict something, and that predict at that time hide this Y test. Do not show the model these Y test actual values, because now you don't have to learn the patterns. Now you have to actually use the learning which you developed. You mean the model developed certain learning about the pattern. So that learning it has to use to predict the values of this Y target variable for this X test. And once the prediction is obtained, then you can check by comparing how far away the predicted values are from actual values. Okay, so that we are doing, we are applying test on our tested model, we are applying on X test. So here my tested model is there, and it has accuracy of 89%, that I know. Okay, and its name is grid search. So grid search is now fitted So perfectly trained. Now apply that grid search for prediction on X test only. Okay. So if you apply, you will get Y predicted. And once Y predicted is obtained, then you don't have to find that mean squared error and all those things by actually calculating like this. That predicted minus actual whole square sigma is equal to 1 to n, or mean absolute error by predicted minus actual in the mode. Python internally does it by just one single line. That is what is the classification report of my Y test and Y predict I have to provide. Y test means what? My actual levels of the test set, and Y predicted is what my machine learning model has predicted. As soon as I click this, a classification report like this is obtained, which shows that this precision, recall, and F1 score, they are the three important parameters for classification. Just like for regression, mean square error, RMSE, and MAE are important parameter, or R square, that is important parameter. Similarly, for regression, for classification, precision, recall, F1 score, and accuracy, these are important parameters. And they are found for each class. So this is precision for class 0, class 1, class 2. Where what is class 0, class 1, and class 2? If I print my this Y again, then you will remember that first all observations have output 0, means they are all setosas. Then these all observations have 1, that means they are all virginicas, and these all have class 2, so that means they are all versicolors. Okay, so I can get the 0, 1, 2 class, that will give me idea about the species. So then this is the precision for setosa class, 100%. 1 means 100%, and F1 score is also 100%. Very good model. That means this is the precision for precision and recall, and F1 score for Virginica class. Second class was versicolor class, and then again 100% for precision, 85% for recall. What is recall and all that? Then don't worry at present. 87% precision and 1% recall. But in short, just remember that this matrix should be as close as possible to 1 or 100% for the best accurate model. And accuracy is 96%, and weighted accuracy is also 96%. So I got a very, very good classifier which had a cross validation score of 89% and accuracy is 96% for classifying this particular iris data set. Okay, I can show you by plotting the graph also of this what this random forest classifier gives. Okay, so this is the plot which I got. This is the code for plotting, and again don't worry about that code, because whenever we will learn PCA, principal component analysis, so at that time we will plot and at that time I would discuss all these steps. But the important thing is that my random forest model very nicely groups the data points into three distinct classes, where this brown colored is versicolor, the green colored is setosa, and there is yellow colored here in this legend it is wrong, but I think the yellow colored, that is virginica, right? So that will give me three species separately. So random forest model has divided into three species. Now I can do the same task without using any supervised method, by using unsupervised method, that is clustering. Okay, so at that time these initial steps would remain the same. What initial steps would remain the same? So let me clear some of the outputs so that space is saved. In fact, this plotting part also let me delete. There is no need of that. Okay, this also I am clearing. This also I am clearing. So initial steps remain the same when I say, then up to this, everything will remain same. That is first, libraries will be imported. Again import. X and Y will be created. Print X and print Y. Sepal length, sepal width, petal length, petal width, and print Y. 0 for setosa, 1 for virginica, 2 for versicolor. Let me clear that also because I need space. Okay, and clear output, and this also clear output. Fine. Now split data, even that step will remain same. Splitting the data. This is just the explanation what PCA will do. So here I had four features: sepal length, sepal width, petal length, petal width. So my data was a 4 column, and fifth column was target column, that was species. Setosa 0, versicolor, that is 1, and virginica, that is 2 coded species were there. So I want to convert it in this 4 column data, or 5 column if I include the target column also, then into 2 column data. Therefore, first I do standard scaling, then I apply principal component analysis. Now I don't want to do supervised, so I'm commenting out random forest, and I now want to do unsupervised k-means clustering. So I remove that commented portion. That means now this part is active. K-means is equal to n clusters is equal to 3. Why I'm choosing 3 clusters should be clear, because I have 3 species. So I want to divide my data points into 3 species. Okay, and thereafter I'm creating my pipeline for unsupervised. So this part will not come. So I can remove, I mean, I will not execute this part. I will execute this part. K-means is created. This is for supervised random forest. Here you can see random forest. So I will not execute it. And this was also for random forest. This is also fitting of random forest. This is predicting with random forest. I will not execute all of them. I will directly go here and create the pipeline for unsupervised. So skip this pipeline for supervised and the remaining steps up to the prediction and create the pipeline for unsupervised. How the pipeline will be created? Same elements. One will be a scalar, standard scalar. One will be PCA, and next will be K-means. Only that is the difference. There next was random forest, a supervised algorithm, and here next is K-means, unsupervised algorithm. Once the pipeline is created, I can fit that to my train model, X-train, and at that time I'm not supplying X test. That you have to understand. Okay, so that means that it is unsupervised. There is no use of labels. Okay, so here if you see my grid search, I am fitting with X train and Y train. So I am using these X train also and Y train also, labels are used. While here, while fitting in the K means, I am just fitting with X train, only the green portion, that is only this portion. I am not using Y train. That is why this is called unsupervised. Okay, so grid, here, X train. So pipeline unsupervised, and if I click that, then I can even see that pipeline. And this is the pipeline. It has one scaling, one PCA, one K means. So as soon as new data enters into the pipeline, it will first be scaled, then PCA will be applied, so that four features, sepal length, sepal width, petal length, petal width, will be converted into just two components, PC1 and PC2. And then K means will be applied with number of clusters is equal to 3. Okay, and then whatever clusters are given by that pipeline supervised, that pipeline we are used to predict on X test. Prediction is always done on unknown data, so we are using it to predict on X test. So let us predict and classify the, print the matrix also. So I am getting the classification score of 0.65 or 6509 means 651, roughly 65.1% of the RAND score. This RAND score is a measure of how good my clusters are. If I get RAND score negative, say if I add one cell, then if I get negative value less than 0, any value, so then my clusters are totally wrong. Totally wrong. But if I get RAND score equals to 0, then my clusters are same as what would be obtained by random chance. And if I get greater than 0, exactly 1, then that is perfect clusters. That means those clusters are representing my data in 100% perfect manner. Now here I am getting 0.65, so at least it is not less than 0. My clusters are not totally wrong. It is not 0 also, so that means they are not those type of clusters which would have been obtained by random chance. So at least they are better than clusters which are obtained by random chance, but they are not perfect also. But 0.65 is reasonably close to 1, so I could say that they are good clusters, not excellent, but good clusters. Okay, so this RAND index, RAND index, that gives the type quality of clustering, and I can plot my clusters, and here I am getting this kind of plots. So earlier the plot was there, I deleted the code, but earlier that plot was there that gave clusters by random forest. This is giving cluster by unsupervised learning, K means, right? And it gives me this kind of cluster. This may be Setosa, this may be Virginica, this may be versicolor. Okay, so this is what the scikit-learn is capable of. How much we have, what capabilities of scikit-learn we have explored? 1, it can provide ready-made data set. 2, it can provide model selection tools like tree test split and grid search CV, which makes the model very robust. 3, it can provide tools for data pre-processing. 4, it can provide tools for decomposition like principal component analysis. 5th, it can provide tools for unsupervised learning, K means. It can provide tools for supervised learning, random forest. It can provide methods for pipeline, so that pipeline would be readily deployed in the next stage deployment. And it can also provide certain metrics which can help me to know how good my classification model is. Similarly, this is just classification example, but it can also do regression with equal efficiency and equal power, right? So scikit-learn is very, very powerful library, and this example was comprehensive example which demonstrates versatility of scikit-learn. It can not only do supervised also, that is regression also. Here we have taken classification, but it can do regression also. It can also do semi-supervised learning also. Okay, so you can understand how powerful this library is. Next part of the chapter is about this exercise, and in this chapter, mostly I am in the mood to give some kind of surprise to you, but that you will see in next lecture. Surprise would be that you will not have to do exercise. I will do exercise live, but using generative AI tools. So that is this kind of tools where we have already OpenAI ChatGPT model and OpenAI API key. And if you don't have that model, then this Llama you can use, and Olama, and here you can use DeepSeek coder or some other like Python uh, for the special coding LLM for Python. Okay, so we will try to use both OpenAI API key and my locally installed Olama Llama models also, and we will at that time see the modern way of doing data science. So thank you, and wait for next lecture and don't miss it. Thank you.